Okay, all right. Good evening, ladies and gentlemen. I know it's evening and you might be a little tired, but this is very exciting topics about the quantum. My kids know about the quantum from the superhero movies. And when I told him, I'm going to talk about something quantum, and he was like, oh, I know, the Spider-Man and the Hulk, and they were all talking about the quantum realm. But this is not different than, when I first learned about this entire quantum, it was very fascinating. Fascinating, and also it went on top of my head before I dig deeper into the whole quantum thing, how it can be part of our networking technologies. So my name is Vinay Saini. I'm principal architect with Cisco Services. I help design networks, enterprise, industrial IoT, anything on recent technologies like quantum as well as AI infra. This is a very short session, approximately 30 minutes. So in that session, we won't be able to go too deep into this, but I'll make sure that you get at least an idea of what is this quantum technology about, what Cisco is doing about this, and where do we stand in terms of network security there. So this is my role. Primarily, I'm a technologist. I'm also author and inventor and the mentor. Some of the books which I have written. One is the Zero Trust, which is coming shortly. It's available for pre-order on Amazon. The second one is non-technical, and I have 3 copies of this book. We have a short quiz at the end of this session, and I'll be happy to hand over to 3 participants the book. So AI is everywhere. If you go around and look, everybody's talking about the AI. And this happened in the last Cisco Live in the Vegas. And I throw a challenge to AI and say, okay, AI, tell me, I'm an inventor, technologist. What do I look like in the parallel universe? Because we're talking about the quantum realm. And it gave this picture. Right? Yeah, same reaction my wife. I told, what do you think about this? And she says, AI was hallucinating. I agree, I agree with that. But then, that's the only AI part in these slides. You won't hear anything on the AI. We are going into the quantum realm. So before we go into the quantum, what is the computing, right? It's all about the computing. We all have the computers faster than quantum, our brain. Our brain is a biological computer. It works on a fraction of the power of a quantum computer or many generations of computers which are coming in the future. We had mechanical in, a few decades back, or I would say like 100 years back. But now everybody's talking about the classical computers. So for this session, anything which is not quantum, for me, that is a classical computer that works on your chips, on transistors. That is a classical computer. So the history of this started with this gentleman, Richard. He was doing some experiment with the quantum physics, and he wanted to simulate something. And then he realized he cannot simulate those states using the classical computers because they can't even understand that. They're not able to have that kind of a permutation and combination. And this guy says, if we want to calculate something on the quantum realm, we need something which is based on the quantum. He gave this idea of calculation based on the quantum physics. And if we think about quantum physics, it's about the spin of an electron, angular rotation of a photon. How do you do a calculation of that, right? People are making calculation out of those computers. So that's how today's quantum computer looks like. They're still infants. They're very similar to the classical computers a year back when they were based on the vacuum tube, So large, so huge. Even today we have. Even the fastest quantum computer today cannot break the encryption. And we'll come to that in a while. So what is a quantum computer? Quantum computing is based on the calculation you make based on the quantum physics phenomenon. Something like superposition and entanglement. So it's not a faster version of your classical computer. It's actually a new way of computing. You're computing based on electrons, photons, and artificial atoms, and so many other things. And a common question comes, so if I have a quantum computer, will I throw my laptop? No, I'm not going to throw that laptop, because you are not going to use quantum computer for everything. You're only giving specific part, which is probability based, to the quantum. You still write a code, even today, on your classical computer, and then you offload certain part of that computation to the quantum computers. The fundamental calculation we are doing in the quantum computer is qubit. We have bit in the classical computer, which can be on and off, 0 and 1, based on the voltage 0 or 5 or any voltage, right? But qubit does not depend on very specific states. You can have n number of states between 0 and 1. That is decided by the coefficients, alpha and beta, what you see. So it means that I can have any states between 0 and 1. It only depends on how much degree of 0 and how much degree of 1 there. But then you will ask, how do we make these qubits? These qubits could be made of atoms, photons, ions. And most of the quantum computers, if you look at, including the one from the IBMs, they are based on the superconducting atoms or ions. So fundamentally what they are is, it's very difficult to excite an electron, put it out of the orbit, and keep it in that state for a longer period of a time. Because of that, they said, okay, why can't we create an artificial atom? So what you see here, the two superconducting layers with an insulator behaves very similar to an artificial atom. And what you saw, the picture of the quantum computer earlier, the big cylindrical type of thing, that is to keep that electron or photon in the excited state for a longer period of a time, because they are very cooled boxes. They do not allow any kind of interference going inside the excited state of that matter. But in spite of that, the coherence time is very, very, very low. That's the reason we are still not able to make the quantum computers of very large sizes. But then what is this? This is like an artificial atom, right? Some alien is there, he says, oh wow, humans finally created an artificial atom, right? That's where we are. But then, this is a mathematical representation of the quantum. So if you read about anything on the quantum physics, it's all about the matrix multiplication, but then you have the coefficients alpha and beta. This is known as the bracket notation. I won't go in depth. This is more of a mathematical calculation. If somebody is from university, they will understand better than me. But then fundamentally, that's how we manipulate things and do the calculations on the quantum stuff. Superposition is another thing where how do you put something between 0 and 1, right? So that concept where you put anything between a state of 0 and 1 to some degree of 0, some degree of 1, that is known as superposition state. How do you do that? Based on what kind of a qubit you have. Typically, you will do with very fine lasers, right? You excite or you change the angle in a certain way, and that decides the state of that. What amount of 0, what amount of a 1 you are putting there. So based on what kind of a qubit you are using, you can do that. So it's nothing related to the voltage and all. You know, we are only talking about the lasers and electrons and the photons, and we are doing calculation out of that. And that's the power. In the classical 2-bit computer, you will have only these 4 states. But in the quantum, you can have 2 raised to power n, because I can have any number of states between 0 and 1. Quantum entanglement is a very interesting phenomenon. So if you entangle 2 qubits, and let's say I entangle them with something called different entanglement. So what it means is, if one qubit is 0, hypothetically, then another will always be 1. If one is 0, then this is 1, this is 1, this is always 0. The beauty is the distance doesn't matter. You can keep them in the same room. You can keep them in different countries. You can keep them on different planets, different galaxy. Einstein even couldn't figure out why this happens, right? But we are making use of that for the networking, for the quantum security, for exchanging the keys, right? The way I understood is, my wife and I, we are quantum entangled, right? So if my wife comes and brings 2 dresses, red or green, she asks me, honey, which one I should put? I say red. Guess which one she will put? Green, right? And distance doesn't matter. Even on the phone, If she asks red or green, I say green. Okay, good. I will put red one. That's how I understood the quantum entanglement. That's a good thing, right? But then the main problem is this quantum coherence, how long you can maintain that state, right? A lot of research is going into this area, how long you can keep something excited there. Because if you don't keep those things in a certain excited state, how will you do calculation based on that, right? How do I do the gate operations, which is coming next? These are the classical gate operations. We all are familiar, right? AND gate, NOT gate, OR gate. Quantum also uses gates called quantum gates, right? This is entire area of discussion. We can spend hours on that. But then at a high level, in order to create a circuit or do calculations, you need something called quantum gates. You have an identity gates, X gate, H gate is Hadamard gate, which you use commonly for putting something in the superposition. So if you look at any quantum algorithm or equation, you see H gate will always be there. And then if you put multiple H gates or I gates, you can come up with an algorithm, which we're going to talk about later. I like this X gate because you have a NOT gate in the classical, where you put 0, you have 1, 1, 0. But we have a C0 gate here, which is controlled node. So that means I will behave like a normal NOT gate only if my input is 1. And this is very interesting because this is where it puts things in the Bell state, right? The entanglement state of this. I know, I mean, you might be thinking what this guy is talking about, but then this is more about the physics, and this is how the quantum computer works, and this is the base of something which is carrying everything, right? This is an example of a quantum circuit. What you see, H gate, and then a lot of other gates, Y gate, X gate, and at the end, you are doing a measurement. And the thing of the quantum computers is, in the circuit, when you measure anything, in the end, it will collapse to either 0 or 1. Any moment, if anybody wants to measure anything, it collapses to 0 and 1. But whether it will collapse to 0 or 1 is actually the very probabilistic thing. And that's what they are saying, you know, if we have a quantum computer with enough qubits, we could have developed vaccination for COVID in just 3 weeks. Because it will try all the permutation combination and give you which is the most probable, you know, thing which interacts and kills the COVID virus or something. But then at the end state, if you're looking at tomorrow, it will be the quantum internet, where you are entangling something, and then you have quantum switches and you're transporting thing. Just before that, you know, I was having interesting discussion with a gentleman in my previous session. They were also looking at why don't we transport actual data using the quantum states? And actually we are doing today with BB84, where we are doing only transferring the keys between the two computers. But then why we are so much worried about, right? I mean, if you search anything on the quantum computers today, the first thing you say, quantum computers are coming. They will break all the encryptions, the internet will be gone, and we will be in what state? Shock state. And there are some predictions that the world will go into recession if somebody tomorrow says they have a quantum computer strong enough which can break encryption. Because everything today runs on the asymmetric keys. Your entire internet is working on the asymmetric keys. Your bank transactions, your certificates, everything is working on that. If somebody can break that, definitely you have a recession. And prediction says you will take at least 1 year to come out of that recession. Not to scare you, but why that is happening? Because today, the entire encryption is based on this fundamental concept. If I have two large prime numbers, I multiply them and use them, you cannot reverse the process and get the two prime numbers. That's the basic fundamental of the encryption. But then, this gentleman, Peter Shor, he came up with a quantum algorithm, right? Using the circuit which I showed you earlier, more complex than that. And he came up with something called quantum Fourier transform. And he has demonstrated that he can break that and bring you back the prime numbers. The only problem is we don't have a strong enough quantum computer who can do the reverse of that for a large prime number. But he has shown theoretically it could be done. So we are just waiting how soon we will get that quantum computer strong enough. But then if you really look at, only the asymmetric encryption is impacted because of the quantum computers, right? Because that's how the Peter Shor's algorithm is able to break the security of the asymmetric. So anything on the RSA, Diffie-Hellman, elliptic curve, quantum computers can break. So what about symmetric, right? Symmetric encryption algorithms are considered safer compared to the asymmetric ones, but you can still break them. I think I have a slide on that, how do you break them? But then symmetric cryptography is still stronger than asymmetric. Usually we don't consider that, right? The problem with symmetric is how do you distribute the symmetric key, right? And most of the solutions, including some of from Cisco, also suggest how you can distribute these symmetric keys in order to safeguard against the quantum attacks. So there is another gentleman, Mr. Grover. He has also proven that you can also break symmetric keys using the quantum. And now you say, okay, symmetric is also broken, asymmetric is also broken. What shall we do, right? But then Grover's algorithm cannot break. It only breaks if your key is of shorter length. So if you have the key size which is more than 256 bits or more, that still gives you enough resistance against the symmetric key thing. But you still have a problem of how do you distribute the quantum safe symmetric keys, right? And most of the solutions around that, if you look at, they are about distributing the symmetric keys. The mechanism could be anything. So here is a quick, just for the reference. I mean, you can see on the slides later which algorithms are safe, which are not safe. Asymmetric, definitely no, but something AES which is symmetric, you have to change the key size immediately in case you have the shorter keys there. And then we have this concept of the quantum key distribution. Symmetric keys, how do you distribute? Imagine you have a scenario, you have two routers, router A and router B. What do you mean by symmetric key? I have to input the same key of both the ends. How do I do that? It's not scalable, right? Or even if it's scalable, how it's very complicated process. So we have this mechanism of quantum key distribution. So where you have two quantum devices which are entangled. Typically it's done using the photon, and we use the fiber spool between them. And then you generate the same symmetric key on both sides. So it's a little complicated algorithm. You can search on the Google. It's BB84. Using that, I change the photon phase a little bit, and I keep sending the stream. So both sides, there is an intelligence which creates the same symmetric key without actually sending anything on the internet. And the beauty of that is, if anybody comes in between and say, oh, I will check what you're going to do, it collapses the state. And there is a nice video on the YouTube where I think somebody in the Europe has tried this. They connected two video conferencing units using this quantum channel, and they deliberately say, okay, can you try to capture the packet? System collapsed and say, oh, somebody's trying to capture thing, right? And that's how the QKD works. But we are talking more in terms of the network security. So in that, you will use quantum key distribution to distribute the symmetric keys. How we do that? That's coming next, right? So there are two ways. How do you secure and how do you create your network, or how do you enable quantum resistance in your network is you can use the quantum QKD devices. Quantum devices are the separate devices. Cisco don't manufacture them, but there are a lot of vendors. We have partnership with them. So they do the entanglement part and the quantum physics part, and we are the Cisco guys. We say, you take care of all the quantum things, you generate the symmetric keys, and we will just use it in our algorithm, right? So we have a long list of the partners, and if anybody want to try, we do that. But then the NIST itself is coming. NIST realized, right? And from the last 2-3 years, there is an active discussion happening. Okay, if asymmetric algorithm itself is so vulnerable against the quantum, we should do about that. So NIST is already recommending few algorithms. Cisco has already implemented that in our SSL algorithms, and we are going to implement very soon with our IPsec, MACsec, and other things. So you don't need anything. Once NIST is there, that should be the end goal. Everything becomes a quantum safe. But we never know. I mean, NIST says something, but then tomorrow some hacker comes and says, I have broke this, right? That's what the scare thing is. Another thing is, how do you transition? By the time PQC comes, there are ways you can still use the PSK or pre-shared key, which is the manual PPK or manual symmetric keys there. So here are some of the easiest thing. If you want to go home now in your hotel and you want to try something, it's still possible, right? How do we do that? So you can simply have a PSK for your IPsec that becomes quantum resistant. If you want a little bit more, the third option, which is the SKS, which is like more of a software-based entropy we generate in our devices and give. And this is based on McLeod's algorithm. Those entropies, not random entropies. So that is considered safe against quantum thing, and you can try that, right? If you want more complicated solution, we support some protocol called SKIP. That SKIP protocol, you can integrate with any QKD vendor. The problem as of today with QKD is the distance, right? So when you're doing entanglement, that entanglement cannot sustain more than few hundred kilometers, right? So, but the last one and the first one you can do, it even works on the virtual routers. If you have a VM, you just download an image. There is a configuration, there is a documentation available on Cisco sites. You configure and then you have a quantum resistant IPsec. And this is how the SKIP protocol works. So this PPK source, it could be QKD or a software-based entropy or even in the cloud, we don't care. Whichever vendor you are talking, we can export the keys from there and import into our routers. It's an HTTP-based protocol. It's an open thing. If any vendor wants to implement, they can do this. And this is the lab which I was talking about. It will take hardly 15 minutes if you want to try. You know how to configure IPsec. There are some additional commands, and it activates that internal RFC, and you can input the key. And you see here the quantum resistance is enabled. But note, this is point-to-point. It's still not point-to-multipoint. If you want to try, there is a document available. Download the code. It works. Now, quantum safe IPsec is supported on iOS XE. Now, some of you might want MACsec, quantum safe MACsec, that is also supported on iOS XR. Same options, you have the PSK, standard PSK. This is a day one feature. You don't have to do anything. If you have a PSK, symmetric key encryption, and you have a quantum resistance enabled. So what I'm saying, I'm not saying quantum safe, I'm saying it's a resistant, right? For actual quantum safe, you still have to wait for NIST or use a combination of NIST and QKD. And again, I think we don't have anything on software here. You need actual hardware if you want to do a MACsec, quantum resistant MACsec. So here are some of the NIST specifications on the algorithms which they are recommending. This is the latest one. I have also kept the reference to the document. And they say if you implement these ciphers and use them in your IPsec or SSL or TLS, it will be quantum safe thing. And we have already implemented this in our SSL code, and we are actually working as I speak on implementing them on the IPsec and the MACsec. All right, now the question comes, where do we start? The quantum computers, are they there today? No, Vinay, you told it, coherence and 100 other problems. But then the scary part is, when the quantum computers will come. If you talk about the government, you talk about the defense, you talk about the finance, they have this commitment to safeguard information for next 20, 30, 50 years. And the problem is somebody can have a dump of your encrypted packet, super secure IPsec tunnel today, right? After 5 years, quantum computer is there and they will disclose all the secrets. So that's where most of the customers I'm talking to, they are from defense, government, banks. Because they know that these are the specific information we are doing between countries, between banks, and we want to save it for the next 20, 30 years. So they are implementing all these things now. But then you can't use all these mechanisms at all the links. So what we do is we tell customers, you have to do evaluations. Number one things, in your security audits, you need to find out how many algorithms are there in your network which are vulnerable against the quantum computers, right? And then you take a call, you upgrade them. You need to have a migration plan. You should have an infosec plan, you know. And then you identify which information is very critical between the two data centers. But even within two data center, is there an information which leaks after 5 years, it will create a problem, right? Anybody from service provider here? No? So SPs plays a major role, right? We all consume SP service, MPLS, VPNs. So when I talk to the SPs, they say, Vinay, you tell us how do we make money out of this, right? Because when people come to us and ask, you give me a quantum safe MPLS connection, I don't know how to do that. Or quantum safe IPsec, I don't know how to do that, right? So if SPs start offering, it's very easy for any enterprise, and you say, okay, upgrade my connection from normal IPsec to quantum safe IPsec, sort of a thing. So the time is now. You have to start looking at the quantum. I was in a conference few days back in Dubai with the government of many countries, and they're taking it very serious, quantum things. So you have to start thinking now. You have to look at what kind of a policies you need to put in order to have the quantum safe solution. So here is a fun part. Now a short quiz, only 4 questions. You can join it using the QR code or go to slido.com, enter this. So this quiz is based on fastest finger first, right answer plus a combination of who gives the answer fast, the top 3 guys. I'll be happy to give the signed copy of my book. I know this is a short session, 30 minutes, so I couldn't go deeper into that. But there is a lot of documentation which is there on the cisco.com. And we also have few breakouts where we go deeper into each of these technologies. We're also working towards having quantum safe VPN. Now VPN, when you talk about, you have point-to-point VPN, you also have a remote access VPN. Some of our customers from the finance, they're asking, how do I have a remote access VPN on the AnyConnect? So we are also working on that. Cool, so we'll take another 30 seconds to let everyone join, and then we'll start the quiz. All right, so here comes the first question. You have 25 seconds. Don't forget, fastest finger first. By the way, Grover is Indian guy, and Peter Shore, I was doing one online course from MIT, and Peter Shore was the lecturer for that. It was amazing what he was talking, but I couldn't understand anything. Okay, 58% got it correct. Ready for the next? Here you go. Ten seconds. That's right, 80% of you got it right. Next one. This should be easy one. Okay, 54% right. And here we have the last one. This is a very important question because if you try to implement and you do an audit, people will ask you, is your solution NIST compliant? Okay, most of you got it right. And here are the winners. Mr. Alexander. Thank you, sir.
Thank you.
AVW and Mr. Domingo. All right, so here is a quick summary. We just have a last slide. What should be our state? Stay informed what is happening because this is a very, very dynamic environment. You might see any day people talking about quantum computer is ready. Something like DeepSeek, right? We know what's happening with the AI. So you have to include the quantum safe solutions. You start experimenting. You identify the vendors. You identify the QKD vendors. You identify the different approach. But then a common thing which is happening, most of our customers are doing is evaluation and assessment. SPs are doing even on the RAN side. SPs are even doing the quantum safe interfaces, right? So you need to do assessment. See what are your weakest link. What are the links you want to go first and make them quantum resistant because you can't do. And then do all these trials in your lab and see which solution is also scalable based on your use case. Like SP, they were looking at rolling out it as a service to make money. But for an enterprise, it could be hub and spoke. I don't know what your topology is, or point to point, which solution is seeking. You're seeking, looking after. The future, we don't know. It could be only NIST, or it could be a combination of QKD and the NIST. There is also an ongoing research because we have a distance limitation on the QKD via satellites. Can I do entanglement over the satellite connection? There are a lot of research papers. If you search on the Google, you will find. That's an open area of research. A lot of dynamic things are happening in this area. So keep and watch out. NIST solution is going to come very soon on Cisco IOS XE, IOS XR routers, even with our AnyConnect solutions. Thank you so much. I hope you learned something, and please rate the session if you like, or give me feedback in case you didn't like something. That's also so that I can improve. Thank you so much.